All right, last one on page 1. So we would take this derivative. And so we have the square root. So the square root of u. Well, first off, sine of x would have to be greater than or equal to 0 in this question, right? So that's going to really limit the domain, right? Because sine is positive between, or 0 positive, between 0 and pi, right? When it's in the first two quadrants, but then it's negative for 2. Then it's going to be positive again from 2 pi to 3 pi, and then negative again, and then 4 pi to 5 pi, and then negative, and then 6 pi, right? So we're going to have this kind of we're going to have this sort of pattern going on there. And also if you go the opposite way, right? So you would also have negative 2 pi to negative pi, right? That would also be a case where sine would be positive. So negative pi, 2 pi to pi to negative pi, right? So there's going to be an infinite number of places where this function is discontinuous. We also know that the derivative of the square root of u is u prime over 2 rad u. So this is going to be u prime, derivative of sine is cosine, twice square root of u, square root of sine. All right, so we're going to get critical values whenever cosine is equal to 0. So cosine is equal to 0 at pi over 2. Cosine is also equal to 0 at 3 pi over 2. 5 pi over 2, 7 pi over 2, negative pi over 2, and so on. But remember, we're not always defined for our function, right? So pi over 2 is in 0 to pi, so we like that one. 3 pi over 2 is in this part of the domain where we don't exist, so we don't care about this one. 7 pi over 2, the same. 9 pi over 2, we like that one. All right, so every, I guess, multiple of 4 plus 1 pi over 2. If we were being like nerdy, we could say like 4k plus 1 pi over 2, we exist, where k is an integer, a whole number. All right, so then we could then also take the second derivative before I just graph this thing. Second derivative, we need some quotient rule here. So we know quotient rule has 5 parts. We have the bottom, just repeated, times the derivative of the top, negative sine of x, minus the top, times the derivative of the bottom, right? So the derivative of 2 sine of x is going to be 2 times this function here, which we already know the derivative, right? So we're going to get 2 cosine of x, 2 radical sine of x. Those cancel, right? So we get cosine squared over radical sine. And then when we square the denominator, 2 rad sine x squared, right? So we're going to get 2 radical sine of x times negative sine of x. We could write that as like sine to the 3/2 power if we really wanted. Minus cosine times cosine minus cosine squared of x over radical sine of x all over 4 sine of x, right? That would be our second derivative. So same issues, right? X is going to be 0 whenever, so the denominator is going to be 0 whenever x is equal to anything that's a green interval. And this numerator is going to equal 0. I don't know. There has to be some times where that thing is equal to 0. So I'm just going to just graph this thing and find our values because I'm getting tired of doing long derivatives, as I'm sure you are. So we would have our f of x. So I'm going to go f of x. There we go. F of x equals what I have initially the square root of the sine of x. And we can see what we knew was going to happen. We can see all those little places where we're going to have no domain. I'm going to take the derivative of this. Right, so I'm going to take f prime of this thing. Right, that's what we found before. That black is cosine of x over 2 sine of x. Right, you can see that as we thought, it's going to go positive to negative, positive to negative. It's sort of tangent, cotangent-ish actually. And then finally, we have our second derivative. So we're going to take f take a derivative. So much easier from a keyboard. Derivative, take another derivative just for good measure, and then of x. Yeah, so that is our function. All right, so we could see that number one, since our second derivative, so I guess the thing is always negative. All right, so since our second derivatives are always negative, this is why our function's concave down. We can see that we're increasing to decreasing. So every place the black hits 0, that's where we have our maximums on our, in this case, purple functions. I'll just take a picture of this thing. Copy this thing over. And paste this in for posterity. So you can look at it. Although I guess you could just like pause like the video and look at this thing however much you want. So maybe I'll do it down here somewhere. Maybe we'll do it up here. This makes for great video. Let's just plop it down right here. There we go. There's our derivative of this function. So we would have again second derivative, first derivative, and initial function.